go ahead and get started because this talk, when I practice, hits right at 40 minutes, and I want to make sure that you don't miss out on any content. So if you are here for fun, friendly computer science, you're in the right place. This talk is going to be your computer science quick hits. So we're going to cover 7 computer science topics in about 35 minutes. And so because we don't have very much time, I'm mainly focusing on fundamental and intro object-oriented concepts. There's a whole world of computer science out there, but I cannot fit it into 40 minutes. If you have familiarity with loops, arrays, and classes, you'll have no problem following along. This is a beginner level talk. My name is Mercedes Bernard. My pronouns are she and her, and I am an engineering manager and senior software engineer with a consulting firm in Chicago called Tandem. My background is in traditional computer science. I have a bachelor's in it from DePaul University, but the longer that I am in this industry, the more I realize that I don't need to know all of that, or at least not to the depth that they teach it to you. If you came into software from a non-traditional career path, whether you went to a code school, you self-taught, you jumped around and tried a lot of different careers, you may have never had the opportunity to learn these items, but you'll still be interviewed on it. And if you are, more of a front-end engineer, interviewing in tech is broken. Many interviewers don't know how to interview, and so even though you might be doing lots of CSS, you might still get asked to implement a linked list. Which, why? You're never going to need to do it. So my goal with this talk is to show you that these topics that show up in interviews and that are sometimes used for gatekeeping aren't intimidating, and they aren't truly that important because A, you probably know most of what I'm going to cover today. You just don't have the right vocabulary to seem like you do. And it's just truly not that important. You can get by without ever learning this. You'll walk away from this talk with a high-level understanding of a bunch of different concepts, as well as metaphors that may help you explain them, and code samples that you can refer to later if you want to dig deeper and you find this interesting. If you're sitting here and you're like, oh, cool, you said this is beginner, I know all of this stuff, I don't need it, I guarantee you there's still something in here that you can take away to help explain this stuff to the people that you mentor. If you are someone who likes visual aids, who would prefer to have the slides up close, especially because there are code samples and I could only do so much to make them fit, you can find the slides here. They've been posted, and you'll be able to follow along there. There will also be code samples in this talk. You can find them all on my GitHub. If you do go pull those down, be sure to check out the commits. I did a very good job on my commits. And so there is a commit for each concept with a great commit message. There's test coverage, so you can go look at unit tests that some of the concepts, the tests actually do a better job illustrating what I'm trying to explain. And all of the code is runnable, so you'll have a working UI to play with if you learn more by doing than by reading. If you are here, I assume you write Ruby code, but I also have a repo for JavaScript and Python if that is what you're more familiar with, or if you just want to see how those compare to each other. All right, so this is everything that we're going to be getting through in the next 35 minutes. So let's go. Do we have anybody here who is really good in the kitchen, likes to cook, likes to bake? Awesome. Don't call me out when I'm wrong, because I'm terrible at it. But if you're good at cooking, there's this thing called cooking with ratios. And so cooking with ratios is where you don't memorize a recipe, but instead you memorize the ratios of ingredients. So you change the proportion of your ingredients according to how much of a thing that you want to make. Big O notation measures the relative complexity of a function or algorithm. Most often, like when you're in an interview, we're talking about running time, but we can truly talk about any computing resource. We can talk about stack depth, we can talk about your CPU, memory usage, all of that. But running time is most common, and so that's what we're going to use for all of these examples. When we're talking about big O, it's also language, hardware, and time agnostic. So if I truly soup up my laptop and the same code runs faster on mine than yours, it doesn't matter. The relative complexity of the code is still the same, and it's all measured in proportion to the input size. When we're talking about big O, we're also talking about it in a worst case scenario. So if somebody says, like, here's a sorting algorithm, what's the big O notation? They don't care that, like, if the collection I handed you is almost sorted, like, it's quicker to sort, because you're like, I just got to flip those two things and it's done. They want a worst case scenario. That's what we're talking about. If you get something that's completely jumbled, what is the worst case scenario in running time to sort it? Okay, so I'm going to break down some of the O's. The first O is O of 1. It's a constant running time, so no matter how your input size changes, it always takes the same amount of time to run. If we're making cupcakes, which cupcakes follow a 4:3:2:1 ratio, fun fact. It's like 4 eggs, 3 cups of flour, butter, I don't know. I'm a bad cook. Don't follow any recipe that you see today. But if we are combining the butter and sugar, we're going to beat them with an electric mixer for 3 minutes. So that's right here. And so I don't care if I'm doing 2 cups butter, 1 cup sugar, 4 cups butter, 2 cups sugar. I always am going to beat it for 3 minutes. So constant time. I don't care what's coming in. It's always a constant time. That's O of 1. The next most common O is O of n. So this is that the running time increases in direct proportion to the input size. It's a linear complexity. And so what you'll see here is if the recipe says, you know, as we add our eggs, you're going to add an egg and beat it with an electric mixer for 1 minute, add another egg, beat it for a minute, add another egg, beat it for a minute. You'll see that if I have to add 4 eggs, it's 4 minutes. If I have to add 8 eggs, it's 8 minutes. It's a linear, it increases in linear time. Now we're getting a little worse here, both in terms of performance and my examples. So if I want to combine the flour, the milk, and the butter really slowly, I don't want chunky flour, I might want to do something that performs in O of n squared time. So O of n squared, like how often are you like, oh yeah, I totally square the input size on a thing. Actually, anytime that you see a nested loop, it's O of n squared. So linear, a good kind of flag for is this O of n is there a for loop or a while loop? You can be pretty confident that's probably O of n. As soon as you start seeing things that are nested, that's O of n squared. If I wanted to beat it even slower, I might add another layer of nesting. The third layer would be O of n cubed, fourth O of n to the fourth, and so on and so forth until why are you writing code that performs so bad? Now, again, let's say that I'm making cupcakes because we are celebrating Fibonacci's birthday. I want to, again, I know, very contrived, but I want to frost Fibonacci numbers on all my cupcakes before I give them to you. To calculate the Fibonacci number, it's O of 2 to the n. This is exponential growth. So the first couple increases in input size, it's not a huge increase in running time, but as you go, it increases more and more, becoming steeper and steeper for the smaller increases, if that makes sense. So calculating the Fibonacci number recursively is an exponential algorithm. It doesn't perform super well. Don't really do it this way, but this is just one example. And then the cousin, at least in my head, the cousin to exponential growth is logarithmic growth. So O of log n, where exponential growth increases more and more and more and more and gets really steep. Logarithmic growth approaches constant time the bigger your input size gets. So at a certain point, you hit like a worst case scenario. It like reaches its worst performance and then pretty much levels out. Divide and conquer algorithms are usually logarithmic. So binary search is one example. If I wanted to extend my cupcake metaphor, I might use a logarithmic algorithm for handing them out, where I have all my cupcakes, I take one, and I give half to you and half to you. You take one, and then you each split it in half all the way through to the back of the room. Like I said, these are getting very contrived. I didn't want to make you sit through that, but that would be one example of logarithmic growth. So when do you use big O? Interviews, it comes up a lot. It just does. And it's one of those things that you can't really piece together with context clues like you can a linked list. It also is really a great mechanism for having a shared language with other programmers to compare the performance of two different approaches to the code. But if you walk away and you don't remember what O of n squared is or what exponential growth is, that's totally cool. If all you walk away with is the more we nest these loops, the worse it gets, that's amazing, and that's seriously the best use case for big O in my opinion. All right, moving right along, we're going to talk about set theory. So Venn diagrams are a great way to think about set theory. A set is a data structure similar to an array, but it's characterized by being an unordered collection, and it has no duplicates. That in and of itself isn't super interesting. Their sets are more interesting by the math that we can do on them, and this math is the foundation of set theory. This is the Venn diagram that we are going to be using throughout this talk. I truly encourage you to go follow those Instagram accounts. They're adorable, and I won't be offended if you're on your phone. So the first set operation we're going to talk about is union. Mathematically, union is written as x cup y or x union y. It is all of the things that exist in set x or in set y, which is why we have everything, because everything exists in one or the other. And in this case, if I were to curate my Instagram feed according to a set union, I would have all of the cute animal accounts in my feed. The converse of that is an intersection, which is x cap y, or x intersect y. And it's the stuff that exists in x and y. So it's only the stuff that exists in both, which is why we have just this stuff in the middle here. So this is when I want all the cute friendships. I only want the accounts that have a cute dog and a cute cat. If I'm a dog person, which I am, I'm very sorry, I might curate my feed using a set difference. So just x minus y. It's the stuff that only exists in set x, nothing that also exists in set y, which is why we get this little like moon shape here. And so this would be if I didn't want to see any cats in my feed, I only want dogs, I would do this. If you are a cat person, you might do the opposite, which because mathematicians and computer scientists love to make everything complicated, they gave its own name too. So instead of just being the other difference, they call it the relative complement, and it gets its own notation, this y/x. And this would give you everything that has cute cats and none of the cute dogs. It is literally the same as y minus x, so like don't let that confuse you. And then finally, we have the symmetric difference. Mathematically, it's x delta y, and so this would be the things that exist only in x or only in y and none of the stuff that's in the intersection. If I can't handle the cuteness of cat and dog best friends, because truly it's the greatest thing, I might say like, I can only handle cute dogs and cute cats, but not both, and this is what I would do. So when do you use Venn diagrams? If you have ever used a relational database, set theory forms the foundation of relational databases. When you're writing SQL, you're doing inner joins, you're doing all of that, you're using set theory in order to achieve it. From a feature implementation standpoint, if you are making website filters on a website, let's say like I'm going to buy shoes, and I say, oh, I can be a 6 or a 6.5 is in the size category, and I want brown shoes. The things that are in the same category are a union, whereas when they're in different categories, that becomes an intersection, so that's also set theory. All right, recursion. So Russian nesting dolls are a great metaphor for recursion because they're all the exact same except for size. If you have never played with them, The dolls continue, you like get the biggest one, you open it, there's another one inside of it, it opens, so you open that one, and then you just keep going until you get to the smallest one, which usually is just like a solid block of wood. It doesn't open, it doesn't do anything, and then you close them back up in reverse order. So recursion is the process in which a function calls itself directly or indirectly, and the function that is doing the calling of itself is called the recursive function. So if you're in an interview and somebody asks you, like, what's the recursive function, it's not a trick question, it's just the one that calls itself. When you are writing a recursive function, we don't want it to call itself indefinitely. Like, we don't want to get ourselves in an infinite loop, have a Stack Overflow exception. It's just not great. So you need to find one case that returns a finite, like discrete value, and that's called the base case in recursion. When you are trying to write a recursive function, the base case is the easiest place to start and then build out from there. So in Russian nesting dolls, that smallest child that doesn't open, that's the base case, and we'll look at an example here. So here we have two functions. We have count, and then we have count nested dolls. So I'm asking you, here's a big doll, tell me how many nested dolls there are. The recursive function here is count nested dolls because that's the one that calls itself. A recursive function almost always takes a parameter or parameters unless you're doing something funky with instance variables or global state in some way, which don't, it's a little confusing. But and so what happens here is we pass in the biggest doll and we open it, and there's a child in it, right? And so we go, okay, there's a child, so I'm going to continue to open it, but when I come back and go to close it up and come out of this call stack, I'm going to remember to add 1. Okay, cool, so biggest doll open, I'm in the next one, I open it, it also has a child, so I'm going to come back down into here, call it again, I'm going to open it, but I'm going to remember when I come back out of this call stack, I'm going to add 1. You continue to do that until you get to the smallest doll. Remember, it's a solid block of wood, it doesn't open. I try to open it, there's no child, there's nothing to open. So I'm at my base case and I return 1. So I'm going to put it back in its parent and close its parent. And remember when I said I closed my parent, I'm going to remember, oh, I'm going to add 1. So I've got 2, put that in its parent, close it, remember I'm adding 1, 3, up the call stack until I'm exited and I handed you 8 dolls or whatever it is. So recursion is just fancy looping. Anything that you can do iteratively, you can also do recursively and vice versa. But recursion, as you might know because it is kind of an intimidating topic, is sometimes hard to read, it's hard to understand, and so nested hierarchies tend to lend themselves best to using recursion to solve them. If you're making a mega menu on a website, you're calculating where you're at in a breadcrumb, you're trying to render a file structure, anything with nested hierarchies, recursion usually works really well because you'll come back, in 6 months and go, oh, conceptually this is how I would model it in my head, this makes sense. Whereas things that are more flat, when you try to do them recursively, can be really hard to wrap your head around because your mental model just doesn't work that way. All right, now we're going to get into the 4 principles of object-oriented programming. So if you're ever in an interview and you get asked what are the 4 principles of object-oriented programming, you will be able to answer this now. So the first one is encapsulation. Do we have any horse people here? Yeah, 1? Okay, cool. Well, then you all won't know if I get this wrong. So horses, I had to do research for this because I didn't know this. Horses have 4 main gaits. They can walk, they can trot, they can canter, and they can gallop. A walk is characterized by a 4-beat pace. It's the slowest of their gaits. Trot is a 2-beat gait. It's a little bit faster. Then you've got a canter, which is a 3-beat gait. It's even faster. And then an all-out gallop is their fastest, and we're back to a 4-beat gait. They move their legs in different orders, sometimes at the same time. Sometimes they start in the back. Sometimes they start in the front. They're all very different. So if I were to make a very fun, exciting video game where I go, I need you to move a horse across the screen, would you want to say, if I go, I need it to walk 30 steps, would you want to know, like, okay, so first they lift their back left leg and down, and then their front right leg and down, and then their back right leg and down, and then their front left. Like, it's, oh my God, please no. That doesn't, I mean, I know the game isn't fun on its own, but that sounds even worse. So instead, I would probably create 4 methods for you to use, and then you would tell the horse, like, walk 30 steps, gallop 70 steps, right? So these methods would encapsulate the state of the horse's legs at any given point in time. This will help make sure that you don't break your horse and somehow end up with 3 legs off the ground when they're not supposed to, and it also gives you just a much better experience. So encapsulation is when you hide an object's state from other objects. You create a public interface, which is just a fancy way of saying a method, for other objects to mutate your object's state. In this case, it's a horse, and the state is where are their legs at any given point in time. But it could be your web component or anything else. Like, what is your state that you don't want other objects to mutate directly because they don't know your constraints, they don't know what they could break. So if we look at what it would look like if I were to encapsulate the horse's state for a canter, it might look like this. A canter is a 3-beat gait, so you can see here I move the first leg up and down, the next 2 come up and down at the same time, and then the last one, I kind of munged the whole idea of how fast they move. But what your user or your other objects would see is they would just get a new horse, and they would say canter for however many steps I told you. So you've completely encapsulated the state of their legs, of your horse's legs, from the other object, but they still get to tell your object, like, I need you to do this thing. So that's encapsulation. Next up is abstraction. When you push a button on a remote control, something happens on your TV, right? So the volume goes up, the channel changes, it turns off, whatever. There are like very few, I mean, nowadays remotes have lots of buttons, but like there are a finite number of things that you can do, and you don't need to know how it works in order for like that thing to happen. So you don't need to know to change the channel that when you push a button, it somehow gets encoded into binary, which then gets encoded into infrared light. It gets sent to your TV. Your TV decodes the light back into binary, sends it to the microprocessor, and then does even more stuff to change the state of your TV. You don't need to know that. You pushed a button, and the channel changed, which is wonderful. So that's an abstraction. Abstraction is an extension of encapsulation, and it can sometimes be really challenging to explain the difference. So abstraction refers to hiding all of the internal implementation details of a class and providing very few clear mechanisms for other objects in the code to interact with it. Encapsulation, you don't let other things mutate the state of your object. Abstraction is you're hiding all of the implementation details of the class or system from other objects. So they're very closely related, but they're slightly different. And you can create different abstractions. So if you've ever been in a code review or just in a team meeting and you've heard somebody go, we made the wrong abstraction, and you're like, but it does the thing, what they mean is that the way that other objects interact with it is not quite right, doesn't quite meet requirements, or is just a little clumsy. If you think about back to the TVs in the 50s, 60s, 70s, the abstraction at that point was like, I want to change the channel, I get up off the couch, I walk over, I turn the knob, and then I go back and I sit down, watch it for 30 seconds, go, that's boring, get back up, go, turn the knob, and sit down. And so in the 80s, we were like, wouldn't it be better if I just push a button? So you made a different abstraction, but the TV's still doing the same thing. Just how you interact with it is different. So, for example, this might be how we programmatically model a remote control. You have a remote and a television, and I say, like, turn on, turn up, too loud, turn down. But what you don't see and what other objects in the system don't see is that all this other stuff is happening. Everything that I walked you through before, where it's handling the click of the button encoding it into binary, converting that to infrared light, sending it to the TV, and then obviously there's all the stuff the TV does to make that happen. All right, we got 1 and 2. On to number 3, which is inheritance. So all garden plants need sun, soil, water to survive. And if you're like me, I have a black thumb. I can't keep anything alive, truly. And so when I go to, for me it's Home Depot, but like whatever store has their garden center, I read those little cards so closely that they like stick in the dirt. So I'm like, I don't want to kill this plant. How much water do you need? How much sun do you need? Like, I'm going to make this perfect, and they still die. But, you know, like, you want to learn everything you can about how to take care of this plant. So if we were going to code up an app that, like, created those little cards from information that we have about all those plants, we might use inheritance to share the code that prints out, like, accesses all of the plant's sun needs, what are their light needs, what are their soil needs, and prints them out in a human understandable like sentence. So inheritance supports reusability in programming. There's a child class, also sometimes known as a subclass, because again, computer scientists love lots of words. And so the child class can inherit all of the fields and properties and methods from its parent class, base class, super class. Pick one, they all are the same thing. It's the class that you inherit from. And so a child class can inherit all of the code from its parent class, and then it can also choose to implement on top of that its own code that either slightly changes the parent class's behavior or just builds on top of it. For example, if we were to make an app that printed out how to take care of each plant, I might have a base class of plant that has some attribute readers for, you know, what is it named, how much light does it need, and then has some methods so that we can print out how to plant it, how to take care of it, and then put it all together in a way that makes sense, where I want to know the name, how to plant it, how to take care of it. And so then if I have children classes of that, which this spot right here over on the side tells it that geranium inherits from plant. So now geranium has access to everything that we saw over here. And then it just has it just has its constructor where it sets its instance variables so that, you know, the geranium is named geranium. And it likes sun, and it likes to be dry. And then that's all you have to do. You don't have to define any of the other methods. But over here, then I can make a collection of plants. And for each one of them, if they all inherit from plant, I can just say, learn how to garden. And so even though I didn't define that method in the child class, because it inherits from plant, it has access to it. And so then it will print out all those instructions in a way that hopefully I will understand and not kill my geraniums. And then the last principle of object-oriented programming is polymorphism. So if you are an avid crafter, I crochet, I love it, it's great. If you do, come find me, we'll chat about it. But you know that there are lots of different crafts that you can use to do essentially the same thing, which is make a fabric. And though like the type of the fabric might be different and the characteristics of it might be different, at the end of the day, you did the same thing. You made a fabric. So if you were to model that programmatically, you might take advantage of polymorphism. So polymorphism is an object-oriented concept where you can use multiple classes in exactly the same way, so their concrete implementation doesn't matter. Inheritance, which we just saw, is one way to achieve polymorphism, where they all inherit from plant, and then I can use that learn how to garden method, and I don't care if it's a geranium or a begonia or whatever. But there are other ways to achieve polymorphism. One is duck typing, so very popular in the Ruby community, and that's where you define the same method name, same signature on lots of different classes, and then you can use all of those classes, and it'll just work. If it walks like a duck and talks like a duck, it is a duck, duck typing. But if you are working in a statically typed language, you may choose to use an interface which just is like a contract that says you must implement these methods with these signatures. And so it's like takes duck typing to a new level where it's just actually enforced. So in our example, we're going to use duck typing. Here we've got a create fabric method. This is on a knitting class. And so to knit, if you want to create a fabric, you knit, wait, is this? Yeah, you knit a row, purl a row, knit a row, purl a row, and you'll create a fabric. But if I don't want to do that, and instead I want to weave my fabric, I still have a create fabric method, takes the exact same argument as knitting, but its concrete implementation is different, right? Because with weaving, you're like weaving a thread over, under, and then back the other way. So you create a different type of fabric. And if neither one of those is what you want, and instead you're like me and you're like, I want to crochet, it's simple, hard to mess up, you don't have to count as much, you might do this. Again, notice create fabric takes the same parameter, but its implementation is very simple. You just make stitches. That's it. You can't mess it up. But when it comes time to actually use them, let's say that I have a little web app that's like, hey, pick your favorite craft, tell me how much fabric you want to make, and we will output it. You'll see here that I'll just read it from the input, whatever the person told me. So they're like, I like to weave. Cool. So I can store the class in a variable here. Doesn't matter which it is. It just becomes this variable. I'll instantiate a new instance of it, and then I can just use it to create fabric. Because they all have that method with those parameters defined, it will work. And so now I've been able to use any concrete class, regardless of its implementation, in the same way, which achieves polymorphism. Awesome, we did really good on time. Great, so if you liked this, I had to cut a section on data structures out of the middle of it, but you can find the slides for it as well as the code samples. I did include the data structures code samples, if you like it, up on my website. And I'm happy to take questions if there are any.